nanohub.org.
Online simulation and more for nanotechnology. You can follow along with this presentation by going to nanohub.org and downloading the corresponding slides. Enjoy the show.
But so I'm testing your ability to listen to me for a few hours, and also my ability to speak for a few hours, but I'm switching subjects now. So we're going to talk about something completely different. We're going to talk about solar cells. So we have a few different faces in the audience, including some experts like Professor Agarwal in solar cells, so it'll be a little more challenging. But what I'm going to try to do is to give a very basic introduction to solar cells. So some of this material, for some of you, will seem a little too basic, because I'm going to explain what an energy band diagram is. And if you didn't know what an energy band was, you probably haven't been following the last few days. So, but there won't be a lot of that. And I mentioned to my wife this morning that I had 69 slides, and she said, "Oh, those poor people." You know? But you know, this is a high level. It's a high level look, and we have 4 more lectures where we're going to delve into it in a little more detail. Okay. So it's an introduction to solar cells, and let me start out by thanking my students. Some of whom I see in the audience here. They've been working very hard over the last few days to get my plots for me. So I want to thank them for all of their help in putting this together. Okay, so, you know, the idea of a solar cell has a long history. You know, in the 1800s, people discovered the photovoltaic effect. You could shine light on materials and get a current to flow. And, you know, Albert Einstein got a Nobel Prize for figuring out what the photoelectric effect was. You know, how the absorption of photons translated into electrical current. But it really wasn't until the 1950s, after the invention of the transistor and semiconductor technology was perfected at Bell Labs, that people started to make reasonably good solar cells, and the field started to be taken seriously as a means of generating electricity. So the first work was done in 1954 by a team at Bell Labs. Oh, I forget now. I mean, this solar cell was 5 or 6% efficient, I think. Basic silicon solar cell. And there were high hopes for the technology. Now, if you're interested, you can see what's happened in efficiencies. If you go to the, this is a plot that's maintained by NREL, the National Renewable Energy Lab. So you can find this somewhere on their webpage, or you can go to the Wikipedia site on solar cells. This is a plot showing efficiencies over time. And I don't have a laser pointer here, but you know, you can see what's happened there. There's an interesting plot down there about 1976. It says IBM T.J. Watson Research Center, an efficiency of about 22%. So that was a record efficiency done by Jerry Woodall, who's now a professor here in Purdue, some of you know about. And that efficiency was not exceeded for something like 15 or almost 20 years by other technologies. That was a gallium arsenide, aluminum gallium arsenide solar cell with a heterojunction. It was very nice work. Let's see, if we look at crystalline silicon, so crystalline silicon is still the mainstream technology. And when I do examples and things, I'm going to be talking about crystalline silicon because it's just the easiest to explain what this is all about. Crystalline silicon, single crystal, are the black squares. And you can see around late 70s, 1980, that blue line is about 15% or so. That's when I left my job at Hewlett-Packard and came back to do a PhD on solar cells. And a lot of very good work got done then. People really dove into the device physics. At that time, people thought it was a mature technology. It had been developed from 5 or 6% for when Bell Labs first demonstrated it. It had been increased to 15% or so when it was used to power satellites. You know, the efficiency gains had saturated. And then there was our first energy crisis in the late 1970s, and people got serious about solar cells. And a lot of very good work was done. We dove in, not only in crystalline silicon, but other materials, and figured out ways to raise the efficiency. And you can see from that blue line with the rectangles there, that the efficiency, the record efficiencies now are up around 24%. So that's a very big increase from 15%, what was thought to be relatively mature, to 24%. it'll be very hard to keep going on that. We've extracted almost every percentage point of efficiency that we can get out of crystalline silicon. Now, but you do see some lines. You see what is that, 42.4% up there. How's that done? That's a material that's a solar cell that uses a combination of band gaps. We'll talk about this a little later. So it uses different band gaps that are optimized to different parts of the solar spectrum. And if you can hook those all in series appropriately and take out the photons that need to go to the right band gap semiconductor, they're much more expensive to produce, but the efficiencies can be remarkably high. And then there are a whole variety of other techniques in there, various types of thin film and polycrystalline, which have respectable efficiencies but are much lower cost. And we'll talk a little bit about that later on. Okay, so if you would like a recent view from industry, Mark Pinto is at Applied Materials, and he has a very nice talk from an industrial perspective about what the future prospects look like for photovoltaics. So you can find that on the NanoHub, so I would refer you to his talk. I'm going to be talking by and large about just some very basics. How do these devices work? And they're incredibly simple, so you might think there's not much to say. It's just a p-n junction with light shining on it, or some kind of junction with light shining on it. But you need a very good knowledge of p-n junctions to figure out how to extract every percentage point of efficiency out of it. So we have sunlight shining on a diode, we make a solar cell. And if we want to understand how this works, we first of all have to understand how a p-n junction works. So we can talk about that in the dark first. And then we have to understand a little bit about how you absorb light in a semiconductor. And then we can put the two together and talk about how a solar cell works. All right. So let's do, we treat p-n junctions in about the first third of a course here on semiconductor devices, but let's just talk very briefly about what a p-n junction is and how it works, because it's not too difficult to understand the basic principles. So you remember, if you have silicon, you have atomic number, 14. You have these discrete energy levels. If you put silicon atoms together in a crystal and all of their wave functions overlap, then all of those energy levels broaden into a band. And each one of them has one for every atom that it originally came from. So we have a band of energy levels that are so closely spaced that the electrons can move between energy levels without thinking about discrete hops. Now, the only bands that really matter to us are the ones near the top. The topmost filled level or band, which is called the valence band, and the topmost empty band. Because under operating conditions, we can take a few electrons out of the valence band, or we can put a few electrons into the conduction band. The deeper levels, the core levels, are just going to remain unperturbed and shielded from us, and nothing is going to change there. So, if we draw an energy band diagram, we only worry about the bottom of the top band, which at 0 degrees is empty, and the top of the filled band, and at 0 degrees, all of those states below the top of the band are filled. And the band gap is a material parameter. For silicon, it's 1.1 electron volts. For gallium arsenide, it's 1.4. Depends on what semiconductor we use. Okay, all right, and then just to acquaint you with some basic terminology in semiconductors. If we just have pure silicon, and silicon these days is probably the purest material that human beings make. It's been refined to enormous precision, very small densities of defects. If we take an intrinsic pure piece of silicon, ideally we shouldn't have any empty states in the valence band, and we shouldn't have any electrons in the conduction band. But at room temperature, there's some thermal energy that can break some bonds and can promote an electron from the valence band to the conduction band. Now we've got an empty state in the valence band that we think of as a positive charge carrier or a hole, and we have an electron in the conduction band. Okay. That's an intrinsic semiconductor, equal numbers of electrons and holes. If we crank the temperature up, we have more thermal energy to break bonds. We get more holes in the valence band and more electrons in the conduction band. Okay, now what's an N-type semiconductor? So if I intentionally introduce an impurity in a semiconductor like phosphorus, which has a valence of 5, silicon has a valence of 4, then there's 1 electron left over. And it's weakly bound then to the phosphorus atom. And at room temperature, we can easily break that bond. So for every phosphorus atom that I put in, if I put in ND of them, I break a bond, and that extra electron is now a free electron to move around in the conduction band. So we would say that that material is doped N-type, and the number of electrons is equal to the number of phosphorus atoms that we put into the silicon. You know, if we cool it down, they might freeze out because there might not be enough thermal energy to break that weak bond to the phosphorus atom. We could do this. We could also make it P-type. So we could introduce a material like boron. Boron has a valence of 3. In a silicon lattice, it wants to be surrounded by 4 nearest neighbors. So it's got 1 too few electrons. So, so in the boron atom, then there'll be, what we can do is to satisfy its bonding to its 4 nearest neighbors, we can pull an electron out of the valence band and satisfy that bond. And now we've introduced a hole in the valence band. So for every boron atom that goes in, we have 1 empty state in the valence band. And the energy to do that is very weak, so the number of holes is equal to the number of boron atoms that we put in. Okay. So now the concept of a Fermi level. And those of you that have been with me for the previous lectures, you know all about Fermi levels and Fermi functions. But for those of you that are brand new to this lecture, let me remind you of what it is. We sort of think the Fermi level tells us how the states are filled up. It's like, you can think of it as a liquid water level. Things below the level are filled, things above are empty. So if the Fermi level is up near the conduction band, it means that at T equals 0, there's an abrupt drop-off. All the states below the Fermi energy are filled, all the states above the Fermi energy are empty. But if there's some thermal energy, then it means there's a small probability of the states above the Fermi level to be occupied, so that gives us electrons in the conduction band. There's a small probability of states below the Fermi level to be unoccupied, but the valence band is way down below it, so there's virtually none. Right? So in my P-type semiconductor, I would draw the Fermi level down near the valence band. It means that most of the states below it are filled, but close to the Fermi energy, there's some probability that a few of them will be empty. So the Fermi level is near the conduction band for N-type, near the valence band for P-type. The Fermi function is given by this expression, and you can see that if the energy is equal to the Fermi energy, the probability that the state will be occupied is exactly 1/2. But if the Fermi energy is located in the band gap where there are no states, then it's probability of 1/2 times 0, so there's nothing there. Okay. All right, and if you look at that expression and you go to energies that are way less than the Fermi energy, that expression will go to 1. If you go to energies that are way above the Fermi energy, that expression will go to 0. All right. Okay, so now back to intrinsic semiconductors again. If I don't have any of those boron or phosphorus atoms, then I've got an equal number of electrons in holes, just thermal energy that has broken a bond. Gives me 1 electron in the conduction band, 1 hole in the valence band. That number we'll call N sub I. It's the intrinsic density of carriers. So that's an important number for semiconductors. And the product of the number of electrons times the number of holes is Ni squared, because each one is equal to Ni. Each one came from that same broken bond. And you might guess that the energy that it takes to do that is related to the band gap. And the probability that you'll break one of those bonds is e to the minus band gap over kT. So in silicon, the band gap is 1.1 electron volts, and kT at room temperature is 0.025 electron volts. So the probability that you'll break one of those bonds is e to the minus 40th. So it's very small. But there are a large number of silicon atoms, 10 to the 22nd per cubic centimeter or something. So what you'll find is that the number of electrons in holes is very close to 10 to the 10th per cubic centimeter in intrinsic silicon. Minuscule fraction of the total number of atoms that are there. If you heat it up to a very high temperature, you can get much more thermal energy, and you can break many more, and you can get lots of carriers. Okay. Now, this is the interesting, so I'm giving you a synopsis of semiconductor physics in a whirlwind, and then we'll talk about solar cells. What if we've doped this by N-type? Then the number of electrons at room temperature is about equal to the number of phosphorus atoms that we put in, Nd. Okay. Now, the thing that we need to remember is this law, N times P is equal to Ni squared. That always holds in equilibrium. That's like a chemistry, law of mass action. So, I know what the number of electrons is. If I want to find out what the number of holes is, it's just N naught is Nd, so it's just the number of holes, P naught, is Ni squared over Nd. So if you take a look at this, in this example, if I put 10 to the 17th phosphorus atoms per cubic centimeter in, that's a moderate doping, not too heavy, not too light. If we put that in, Ni is about 10 to the 10th. So the number of holes is 10 to the 10th squared over 10 to the 17th. So the number of holes is 10 to the 3rd. Now we've got even fewer than we did in equilibrium. And it works the same way if I have a p-type semiconductor. Now I know that the number of holes is equal to the number of boron atoms that we intentionally put in. But Np is still Ni squared. So if I put in 10 to the 17th boron atoms, I'll end up with 10 to the 3rd electrons, such that the product of the two is equal to Ni squared. Okay, so now we can get to a p-n junction. A solar cell is a p-n junction, right? So we have to talk about what a p-n junction is. So a p-n junction, we just bring an n-type and p-type semiconductor together. So this isn't the way you make a p-n junction, but it's a nice way to conceptually think about it. We have an n-type semiconductor, we have a p-type semiconductor, we bring the two together and we ask what will happen. Well, this Fermi level, if we think about this as like the level of a liquid that's filling up the states, and the top surface is the Fermi level. If I bring the two together, it's like you've got two separate lakes at different levels. You dig a channel between the two, the water will flow and the water level will equalize. In equilibrium, there's only one Fermi level in one position. So when I bring these two together, I can only have one Fermi level, right? When they're separate, I have two isolated systems. I have two different Fermi levels. So if we bring them together, that's what happens. So if we want to draw the energy band diagram for this p-n junction, we start by drawing a straight line for the Fermi level because we know it's constant. And I'll just ground it over here, and I need some reference somewhere. It can be arbitrary. So I'll say it stays where it did. What was that side? Was that my p side of the semiconductor? Okay, now if I draw the energy band diagram, I'll draw something like this. If I get way to the right, then I won't know that I've made a junction. And it'll just be a p-type semiconductor with the Fermi level down by the valence band. If I get way to the left, it's just an n-type semiconductor that doesn't know that there's a p-n junction over there to the right somewhere. So the Fermi level has to be by the conduction band. And then I just smoothly draw a line from one to the other. That's the energy band diagram of my p-n junction. Okay, so you can see that in the transition region, the Fermi level is a long way from the conduction band, which means there are very few electrons, and it's a long way from the valence band, which means there are very few holes. So people call that a depletion region. And physically, you can think that the holes have diffused in one direction, and the electrons have diffused in another direction, and they've left behind this depletion region where there aren't very many carriers. Okay. Now, how did this all happen? What we had for an electron has a minus charge. So if you apply a potential, you'll lower the electron energy by minus Q times the voltage. So this movement of charge set up an electric field that set up a potential difference between the n-type and p-type that lowered the energy on the n side and pulled the n side down so that the conduction band will come down and be where it's supposed to be with respect to the Fermi energy. So there must be a positive voltage that developed on the n side. Okay. That positive voltage is called the built-in potential of the p-n junction. And this is a really interesting voltage, that we talk about a bit when we do semiconductor courses. You have a p-n junction, you go in the lab, you put your voltmeter across the p side and the n side. What do you measure? Nothing. But the voltage is there. All right? And this takes a little bit of discussion that maybe we can do at the break or something. What you argue is that what the voltmeter really measures is the difference in Fermi levels. It doesn't measure the difference in the electrostatic potential. What it really measures is the difference in the Fermi energies. And in some cases, those are the same things. But when you have junctions and you have built-in voltages in equilibrium, they're not the same thing. You can see what would happen if that was a real voltage. I would just attach a resistor across there. There would be voltage across that resistor. Current would flow, would be given by Ohm's law. I would be delivering power to a load. I'd have a perpetual motion machine, right? Something would be wrong. But there is a potential drop there, and it's central to the operation of this device. And, we can measure it with special techniques and things. And another thing to think about is you can see that potential drop is about the band gap divided by Q, the band gap in electron volts. Because the Fermi level in the valence band, in the p side was near the valence band, the Fermi level in the n side was near the conduction band, I have to establish a voltage that lines those two. So it's roughly the band gap that it takes to move those two into alignment. And you can get this simple little expression if you derive exactly what it is. Okay. And one of the other things that we teach students in beginning semiconductor courses is that the variation of that energy band is occurring because there's a variation in the local electrostatic potential. So the slope of that is the gradient of the electrostatic potential. It's the electric field. So if you look at the gradient of that, you can get the electric field. You can see it's positive there. So you can think of the electric field as exerting a force on holes to the right, which stops them from diffusing and stops current flowing. And it exerts a force on electrons to the left, which stops them from diffusing away from the N region. And that's what establishes equilibrium and stops the current from flowing. And then we draw this little circuit diagram here, where the arrow points from the P side to the N side, always. All right, that's our convention. Now, let me look about this in equilibrium a little bit more. So, I have this potential barrier that got set up. This is what keeps the electrons on the N side and keeps the holes on the P side, that when this charge sloshed around and moved apart and set up an electric field, it set up a potential energy barrier that holds all the electrons on the N side and all the holes on the P side. But still, things are happening at a microscopic basis. If I look at what's really happening, electrons have a probability of hopping over that potential barrier. Right? And then some of them will just drop down the potential barrier. And those two processes just balance in equilibrium so that we get the right number of electrons in equilibrium on the P side and the right number of holes on the N side. Now, what is that probability? Well, there are lots of problems in physics where you ask, what's the probability that you can get over a barrier? Or you ask the things like, if you know the density of oxygen molecules on the surface, what's the density 50,000 feet higher? Well, it's e to the minus gravitational potential, mgh, e to the minus barrier height over kT. In this case, the barrier height is that Q times VBI. So the probability that an electron will get over that is e to the minus 40, because VBI is about 1 electron volt. Very small. But a few of them will get over there, a few of them will drop down, just enough to balance everything out and keep it all in equilibrium. Okay, now we go under forward bias, because our solar cell is going to develop a voltage and deliver power. So if we apply a positive voltage to the P side, positive voltage lowers electron energy, and these are electron energy band diagrams. So a positive voltage on the P side is going to pull everything down. And if I pull everything down, it means that that potential energy barrier is not as high as it was in equilibrium. It's the built-in potential of about 1 volt minus whatever forward bias I put on it, If I put on a half a volt, then the potential energy barrier is a half a volt. Okay, now the probability of getting over that barrier is much higher. It's still e to the minus barrier height over kT, but the barrier is much smaller. So the probability is exponentially bigger. So in fact, the probability is the equilibrium probability times e to the q applied voltage over kT, right? Which kT is small, so you apply just a few tenths of a volt, that can be a very big number. What it means is it's much easier now for electrons to get over that barrier, so we're going to be out of equilibrium on the n side. We're going to have many more minority carrier electrons on the n side than we did in equilibrium, because they can hop over that barrier from the n side and get to the p side. Okay, same thing, we'll have many more holes on the n side than we did in equilibrium, because holes, the whole energy goes down, so the whole energies hop over a barrier by going down. Okay, so the important point here then is that there is a lot of what we would call excess charge on the n side. There are excess electrons that weren't there in equilibrium. And we're going to ask the question, what is the total concentration of excess electrons in the p region? So we would just integrate from the beginning of the p region to the end, that total concentration. And if I want to find how much current flows, current is charge divided by time. So that excess carriers, it's the current, I know it's going to be charge divided by some time, and I'll have to figure out, what does that time mean? But current is always charge divided by time, so I'll just have to figure out what the time means. Now, at the same time, I'm injecting excess holes onto the n side, so there's some excess hole charge Q sub p, and it will give me current also, and I just add the two up. Okay, now, as we'll discuss in a minute here, this time is actually the average time it takes for one of these electrons or holes to recombine, and I'll talk about that in a minute, or it's the average time that it takes to diffuse to a contact where it will recombine quickly. So I'm kind of suggesting that every time an electron-hole pair recombines, I get current through my diode. Right. So let's see how that works. So this is an important point that I use to try to understand solar cells. It's recombination leads to current. So we have a forward bias diode. We've lowered that barrier. Electrons can get injected over, and now we have a population of excess minority carrier electrons in the p side. Now, they can recombine, in a number of different ways. But one way they could recombine is that there could be a defect. Even though silicon is very, very pure, well, for solar cells, you like to use less expensive silicon, so it's not as pure as it could be, but it's still very good. But there are defect energy states inside the band gap. An electron could hop down into that and then hop down again and fill up a whole state. So that's a dominant way. It could just hop directly from the conduction band to the valence band, and that happens more. In some semiconductors, that's the dominant way. In semiconductors like gallium arsenide and 3,5, that's the way most of them occur. And then that energy that they lost in dropping down in energy is given off as light. That's how you make a light-emitting diode. In materials like silicon, that's not the strongest recombination path. It's through these defects. And the excess energy is given up to phonons, and it just heats up the lattice. Okay. So let's see what happens, when that happens. The electron drops down, fills up the hole. We've now lost a hole. The p side was happy. It was electrostatically neutral. It had just the right number of holes and just the right number of boron atoms that were ionized. That's where the holes came from. Everybody was happy. Now we've destroyed a hole. There's an electrostatic imbalance. The system doesn't like that. So it reacts immediately by kicking an electron out of the valence band to create a hole. Now the p side is happy again. But the n side isn't happy because it was electrostatically neutral. It had just the right number of electrons to be electrostatically neutral and balance the charge of the phosphorus atoms that were ionized to give us that electron. Well, that one electron flows through the power supply around the other side, comes in the conduction band of the n side, and replaces the missing electron. So you can see anytime an electron or a hole recombine, one electron flows in the external circuit. So diode current is all about recombination. Now, the electron might be able to diffuse all the way to the contact, and the contact is usually a highly defective region. There's a lot of traps and interface states and a lot of ways it can recombine. If an electron gets to the contact and recombines quickly there, the same thing happens. It doesn't matter whether it recombines in the bulk or whether it recombines at the contact. All that matters is that it recombines and we send one electron around the external circuit. Okay. So here's a summary of how the forward bias diode works. We lower the potential energy barrier by applying a positive voltage on the P side. That allows us to more easily, electrons can more easily hop over the barrier. We now have an excess population of electrons on the P side. Those excess electrons, the system always reacts. It's out of equilibrium. It always reacts by trying to restore equilibrium, which means the system will try to promote recombination to get rid of those excess electrons. When they recombine, then one electron flows in the external circuit. Okay. So now we can develop an equation for the IV characteristic. So current is charge divided by time. That Q sub n is the total number of excess electrons on the P side. Q sub P is the total number of excess holes on the N side. And tau is the characteristic time. This is either the time it took to recombine through the defect or the time it took to diffuse to the contact and immediately recombine at the contact, whichever one is shorter. Okay. So the charge is going to be exponentially proportional to e to the QV over KT. In equilibrium, we have this relation NP is equal to Ni squared. The equilibrium charge of electrons on the P side was Ni squared over the P-type dopant concentration. When I lower the barrier, I increase that by e to the QVA over KT. The -1 is so that when I'm in equilibrium, I don't have any excess charge. Q is only the extra charge, not the equilibrium charge. Okay, so my ideal diode equation, you can see that if I just take T or Q and divide it by some T, I'm going to get an equation that has some constant out front times e to the QV over KT minus 1. So people call that either the Shockley diode equation or the ideal diode equation. That's the simplest form of the description of the ideal diode equation. Now, more generally, if you worked with p-n junctions a little bit, you know that you put a factor n in the denominator and you write the diode current as e to the QVA over nkt. So we've described a process that leads to a current that has an n equals 1. There are other processes that lead to n equals 2. And I don't remember whether I discussed that in this talk, but I surely discuss it in the next one. But I'll have to remind myself about what's on board here. So in practice, if you measure a diode, you should expect to see a diode ideality factor between n equals 1 and n equals 2. If you get something that's like n equals 1, you say, I have an ideal diode. Okay, so dark IV, let's see. Okay, so let's take a quick look at here. This is a generic solar cell. So this is a generic, not a record efficiency silicon solar cell, but something that might be manufactured at reasonable cost. So the dimensions and doping are fairly reasonable. It's built on a p-type layer. It has a very heavily doped p-type layer on the back, and I'll discuss that in a minute, and then a bottom ohmic contact. It has a very thin n-type layer in the bottom. Actually, 0.3 microns is not all that thin, but it's relatively thin. The whole wafer is about 200 micrometers thick. And, I can't put a metal contact across the whole top surface where I wouldn't let light in, right? And I'm trying to make a solar cell. So there's a metal grid of fingers, and you try to design the grid such that you obscure less than 10% of the area with the metal grid. If you get it too fine, you'll start adding some resistances and things. Okay, so if I draw an energy band diagram, if I look near the front region, it's just like that energy band diagram that I sketched. This is a simulated one with a program called ADEPT, and you'll hear about that tomorrow. Professor Gray will talk about it. But you can see it looks just like the one we sketched. The N-type layer is doped pretty heavily, so the Fermi level is actually inside the conduction band. The P-type layer is doped moderately. Now, if I go way back to the end, remember there was this heavily doped P-type region at the end. So if I go way back at the end, the whole structure is 200 microns thick. If I go back in the final 1 micron, or 0.8 of a micron, you can see that when the valence band gets closer to the Fermi level, it means that I have more holes. So you can see the heavily doped region right at the back, and then you can see it's a little bit more lightly doped there. And actually, this is something that we'll talk about in my lecture tomorrow. You can see an energy barrier there. We're going to insert excess electrons in the conduction band. And you can see that there's an energy barrier there that they have to hop over if they are going to get to the contact. That's designed to keep them from getting to the contact, because the contact is a defect where they recombine. It's called a minority carrier mirror. Okay, so if you look at the IV characteristic, again, this is a simulated one using realistic material parameters and lifetimes and things. If you look to the left, you're on a linear plot, and you might remember it takes about 0.6 of a volt to turn a silicon diode on and for significant current to start to flow. But if you look at it on a log plot, that's the green plot, you can see even below 0.6 of a volt, there's a lot of current flowing, and you can see it on a log plot. If you look very carefully here, you'll see that there's a region in the middle where n is almost exactly 1. And I explained the physics of what that was with those simple arguments earlier. If you look down at lower voltages, you can see a region where it's starting to increase. And depending on the band gap and the lifetimes and things, it could go all the way to 2. In this case, you're just beginning to see a hint that something else is going on. We'll talk about that tomorrow. And then you see the dip down, and what you're seeing there is just that -1 in the e to the qv over kt minus 1. If you go up to higher voltages, you can see it's starting to roll off just a little. So n is a little bit bigger than 1. And that can happen for a couple of reasons. The most common one is that there's a series resistance. And we'll talk about that later on also. Okay, so these are plots that I'm going to go through carefully tomorrow, but I just want to make a point here that I argued that the current is related to recombination. So in order to understand the device, you'd like to understand recombination inside the device. So the blue line is the recombination rate. Now, you'd also like to know where are those carriers recombining, because if you want to change the performance or improve the performance, you might want to go in and re-engineer the cell to shut off some recombination mechanisms. The green line is the integrated total. Now, you can see that there's a bunch of stuff happening right at the beginning at that first 0.3 of a micron that you can't see. And there's a bunch of stuff happening at the end where it looks like the green line plot goes from 0 to 1. That's 100% of the recombination. You can see that an awful lot of the recombination is occurring at that back contact. That little barrier we put there isn't keeping the electrons away. And if I look in the front, I can see that there's a significant amount of recombination in the front. 2 orders of magnitude bigger than what's happening in the P region. That's because the lifetime is very, very short in that very heavily doped material. So it's recombining very quickly. Okay, so there's a lot of information that we can get out of that, and that's sort of the subject of the talk tomorrow. I will mention that roll-off region. I've described this ideal diode, but you put metal contacts on P and N-type silicon, you're going to introduce some contact resistance. So really, any real device that you measure in the lab, you'll have a series resistance, and you'll only be able to apply your voltage to those 2 white terminals there. Meaning that when some of the current flows, it'll be lost across that series resistance, and the actual voltage that gets applied across the diode, V sub A, the applied voltage across the junction, will be less than the voltage that you apply across the terminals of the diode. And as you get higher and higher in current, you'll lose more and more of that voltage you're applying in that series resistance. And that's what causes things to roll off. So here's a simulation of that same solar cell. When you have a series resistance of no ohms, you get that red dashed line that we showed earlier. If you put 100 ohms in, you'll get that blue line, and you can see it starting to roll off. So one of the things that people try to do in solar cells is to minimize that series resistance as much as possible. So we'll talk about that later on too. Okay, so that's how the IV characteristic works in the dark. When I did my PhD thesis, I basically worked on dark current of solar cells. And I would go home and my wife would say, "What did you do in the lab all day?" And I said, "I'm working on the dark current of a solar cell." And she thought this was the silliest thing to do. You know, you shine, the whole point of a solar cell is to shine light on it, and why are you working on the dark current? Now I'll explain in a minute here. But let's talk about optical absorption. So just a few fundamentals. So, you know, the idea is this. Light comes in, it's got some wavelength. It's got some energy that is Planck's constant times its frequency. If the energy is bigger than the band gap, it can promote an electron from the valence band to the conduction band that will leave behind an empty state in the valence band, so now I've got a hole, and it will give me an electron in the conduction band. So whether or not that happens will depend on the energy of the light that comes in. So the energy must be big enough, or the wavelength must be short enough such that I've got enough energy to create an electron-hole pair. Okay, so we have to think about this spectrum. You know, the solar spectrum is roughly, I think, a black body of about 6,000 degrees Kelvin, I guess, you know, roughly, approximately. If you go in outer space and measure the solar spectrum, so this is the amount of solar power in each little wavelength integral. This is called air mass zero because there's no atmosphere for it to go through and be absorbed. So the solar spectrum will look like this. You can see some sharp lines here that have to do with things in the solar atmosphere. And if you integrate the power, you get 136 milliwatts per square centimeter of solar power. And when you make a solar cell, you want to compare that to the electrical power that you get out and maximize the efficiency. Now, if you look on the surface of the Earth, you'll get a slightly different solar spectrum. And it will depend on how much atmosphere you have to go through. So that's going to depend on the latitude that you're at and what angle the sun is at. So people measure this thing, they call it air mass. It's 1 over cosine of the angle to the normal. And air mass 1.5 is sort of a typical condition for mid-latitudes in the US, or mid-latitudes anywhere. And it corresponds to a latitude of 42.8 degrees, right? So you have to go, if you're at the equator and you're going directly through, you don't have to go through as much atmosphere. If you're up here at our latitude, you have to go through. And there are various, you know, gases, species, water vapor in the atmosphere that have absorption at particular frequencies. So if you look at the blue line, you can see that we have these notches where the solar spectrum that came in is strongly absorbed in these certain bands. So it's the blue line that's going to be the incident power for our solar cell if we're making a terrestrial solar cell. And the G there means global. So when people do these measurements, there's a lot of diffuse scattering in the atmosphere. So the beam that's coming down is not just a direct beam. There's some diffuse scattering too. So when they do these measurements, they include that. So AM 1.5 G means it includes all of those global and diffuse effects as well. And the total integrated power is exactly 100 milliwatts per square centimeter. So you may ask, how can it be exactly 100 milliwatts per square centimeter? Well, it isn't, but it's just a standard. So people have adjusted this spectrum so that it's exactly 100 milliwatts per square centimeter, and everybody compares their efficiencies to a spectrum like this. Its intensity has been adjusted so it's exactly 100 milliwatts per square centimeter. So if you get 10 milliwatts out of your solar cell, you know you have a 10% efficient solar cell. Okay, so then you can ask yourself, well, how many photons can be absorbed? So if your solar cell is made out of silicon, the band gap is 1.1 eV. So only photons with an energy above 1.1 eV can be absorbed, or that means only photons with a wavelength below something. That turns out to be close to 1.1 micrometers. So if I look at that same solar spectrum, I can only absorb the photons that have a short enough wavelength. Those are the ones in yellow. Right? The rest of them are totally wasted. They contain power, they contain part of that 100 milliwatts per square centimeter, but I can't take advantage of that in silicon. It just goes through. So the total number of photons per square centimeter per second that I can get, if I collect every one of those, is 2.761 times 10 to the 17th, and that corresponds to a current of 44.24 milliamps per square centimeter. These high efficiency silicon cells are getting remarkably close to that. Okay, so what happens to all of those? A lot of those photons have an energy more than the band gap. So they put an electron way up in the conduction band somewhere. Then what happens? Well, what happens is it emits optical photons, sheds that energy, and it just heats up the solar cell. That's all wasted, right? So that's one of the problems that you have in these solar cells, is that you're just wasting the energy of any photon that has more energy than the band gap. So there are a lot of people that think about, are there ways to prevent this from happening? One way is to use a lot of different band gaps and just take a slice of the solar spectrum and use the right band gap for that right part of that spectrum. That's how those over 40% efficiency solar cells are made. But people also think about, is there some scheme that I could get that electron out before it loses all of its energy, and then I wouldn't waste it? Those are ideas that fall under this category of third generation PV. Okay, now the question we have, potentially, every photon with an energy above the band gap could be absorbed. But if I have some finite thickness of solar cell, not everyone will actually get absorbed. Some of them won't have a chance to. So here I'm just pointing out that the incident flux is going to decay as e to the minus alpha x. So it'll decay exponentially with position. And alpha is the optical absorption coefficient. If it's greater than 0, it means electrons are being absorbed. So I can compute the generation rate, because as the flux decays, the reason it's decaying is because electron hole pairs or photons are being converted into electron hole pairs. So I can just differentiate that position dependent flux, and I get an expression for the generation rate versus position. Now that's at a specific wavelength, so then I have to integrate over that complicated solar spectrum. But all of that's easy to write a MATLAB script, and these are things that my students did for me in a few of these plots that I'm going to show you. Now, so your question is, what determines alpha? And this gets into some semiconductor physics that we won't be able to go into deeply, but this gets into the details of the band structure. So remember, for a classical particle, energy is momentum squared divided by 2 times mass. Now, in a semiconductor crystal, the momentum is really the crystal momentum, h bar k, and we have some complex band structure, but it oftentimes looks something like that. Now, when the minimum of the conduction band and the maximum of the valence band occur at the same momentum, at 0, we call that a direct band gap semiconductor. Now, it turns out photons carry very little momentum. So I can make vertical transitions there, come in with an energy bigger than h nu, I can make a transition up, and I can conserve momentum, and it's no problem. Materials like this absorb light very efficiently. Now, if you have silicon, it's what's called an indirect gap semiconductor. The minimum in the conduction band is at a different momentum than the maximum in the valence band. The photon doesn't have much momentum. So in conserving momentum, in exciting an electron from the valence band to the conduction band, what you have to do is to find a lattice vibration with the right momentum, so that it's an extra interaction with a lattice vibration. That's less probable. So the absorption coefficient is going to be weaker. So it's not going to be as efficient in absorbing as a direct band gap semiconductor is. So here's an example. So SIGS is a material, copper, indium, gallium diselenide is a material that is widely used for photovoltaic applications. Professor Agarwal's lab does a lot of work on it over here at Purdue. Silicon is also the most common commercial technology still today, although some thin film materials are making significant inroads. If you look at the percentage, these are the percentage of photons absorbed. You look at just the photons above the band gap. What percentage of those are absorbed versus thickness of the absorbing layer? You can see that for SIGs, that's a direct gap material. 1 micron will absorb 90% of all photons that can possibly be absorbed. For silicon, I have to get closer to 10,000 microns of silicon if I want to absorb every photon, because the absorption coefficient is much weaker. It's an indirect gap semiconductor. So if you're looking to minimize material costs for low-cost photovoltaics, you'd like to use a direct gap semiconductor because a very small amount of material can absorb all of the photons. Silicon, it takes a very much thicker layer. Okay. So to get as many electron-hole pairs generated, we have to get the light in. So people do things like anti-reflection coatings to make sure you get as many photons in. And then you want to make the solar cell as thick as possible. But sometimes there are tricks that you can use to make it effectively thick. And this is one of the ways. So this is a record efficiency silicon cell from Martin Green's group at University of New South Wales. It's over 24% efficient. It's only got 300 to 400 microns of thickness of silicon, so it can't absorb all the photons. But if you look at the structure, it has a set of etchings there along 111 planes, so that it gets inverted pyramids. It creates this structure in silicon such that when the light comes in, if it doesn't get absorbed, if it doesn't get transmitted into the silicon, it gets bounced off into another one. It's got a chance to get transmitted there. So it has a very low reflection coefficient. Once the light gets in, if it goes all the way to the back and it hasn't been absorbed yet, you can see that most of on the back surface there's a thin layer there labeled oxide. That oxide layer is about a half wavelength thick, so that when the photons go down, reflect off the metal back contact and come back, they interfere in phase. So it's a layer that's designed to maximize reflection. They go back through and they make a second pass. When they make a second pass, they hit most of those inverted pyramids at an angle that's above the critical angle, so they're internally reflected and they stay in. And they go back down and they reflect out again. That's called light trapping. So it can make a physically thin layer of silicon appear to be very, very thick, so we get a chance to absorb the photons. Okay, so we've generated the electron-hole pairs. We have to collect them. If we collect them, then we have a p-n junction. So the way we collect them is we just see that if we create a minority carrier electron on the p side near the junction, it'll just fall down in energy and go over to the n side. So the p-n junction collects the carriers. That's why we use a p-n junction. So we have a layer. Usually the top layer is relatively thin. That was 0.3 of a micron in my example. The absorbing layer is thicker, so we can absorb all of the photons. And what we want to be careful of is that the photons that we absorb, the minority carriers that we generate, have to diffuse to the junction so that they can be collected and go out to contact. Now, some of them might recombine at a defect before they get to the junction. Some of them might diffuse backwards to the back contact where they can recombine. So you want to engineer the structure so that most of them diffuse towards the front and are collected. So a parameter that people will talk about is the collection efficiency. So it's if JL max, so if I know how many electron-hole pairs are generated, I multiply that by the charge on the electron. That's the maximum current I could ever get. The current that I actually get out, J light, is a little bit less than that, and that ratio is called the collection efficiency. For a high-efficiency solar cell, you want that to be well over 90%. Okay. And I'll just mention, one of the nice things about a silicon cell is that you don't expect this collection to have much to do with the voltage. It's just going to fall down that barrier. You know, if I apply a forward bias and I make the barrier a little smaller, it'll still fall down that smaller barrier and go out the N-type. So the collection is relatively insensitive to the voltage that I apply across the diode. Okay. And I'll just mention briefly, these electrons that are generated away from the junction, they typically diffuse. Before they recombine, they can diffuse on the order of a diffusion length, which is the square root of diffusion coefficient times time. So we want a material that has a high diffusion coefficient or high mobility, or a material that has a very long lifetime, so it has plenty of time to diffuse to the junction and get collected. Now that's one of the reasons that you can't make the layer as thick as you want, because if you make it too thick, it'll be more than a diffusion length away from the junction, and it won't get there. So that's one of the reasons that when people design cells like this, you try to keep the absorbing layer physically thin so that once you generate an electron-hole pair, it can diffuse to the junction and get collected. Okay, so now we can talk about a solar cell. We've done it in the light and we've done it in the dark. So here's how it works. The light creates an electron-hole pair. The p-n junction collects the electron-hole pair. The electron goes out the n contact. An electron going out the n contact runs around the external circuit and comes back in the p-type. And that gives us a current that flows opposite to the direction of the arrow. So the direction of the arrow tells us the direction that the current flows when we apply a positive voltage to the p side. That's a forward bias junction. The light-generated current flows in the opposite direction. So current flows, it's flowing in the opposite direction of the arrow. It flows through that resistor R, which is the load that we're delivering the power to. We're trying to do something useful with it. That creates a positive voltage that gets applied to the positive side, that forward biases the diode and gives me a current that goes in the other direction. So the net result is that I get some combination of those two. So that forward bias lowers the barrier, and now some electrons are being collected, but other electrons are hopping over the barrier in the opposite direction and going to the p side. So what I get is the combination of the two. And the simplest way I can think about this is it just behaves like a superposition. So I had the current in the dark. We discussed where that comes from. Now we have a current in the light, and I discussed that it's more or less independent of voltage. It doesn't matter how big that barrier is. Once an electron gets close to it, it just falls down the barrier and goes out the n-type contact. If I want the total IV characteristic of the solar cell, I just add the two, and I'll get a characteristic that looks like that. Okay. So that's why I worked on dark current for my PhD thesis, because then if somebody tells me what the light current is, I just have to add it to the dark current, and we can understand how the solar cell works. So if we look at this again, you can see that, first of all, you can see that the current is negative, the voltage is positive. That means that the power, which is the product of the two, is negative. What does a negative power mean? It means I'm not dissipating power in the diode, I'm generating power. Now, if you look down at V equals 0, the power is 0. We have a lot of current but no voltage, so the power is 0. If I look at the open circuit voltage, where no current flows, I have a lot of voltage but no current, so there's no power there. Somewhere in between, I get maximum power. That's where you want to operate the device. And that's called the max power point. And you can see that it's less than the product of the short circuit current and the open circuit voltage. And it's less by a factor people call the fill factor. And the fill factor is something that you can't do a whole lot about. It depends on the shape of the diode characteristic, which is the Shockley diode equation. You can make it worse, but you can't make it better very easily. And then the efficiency then is just the power out, which is the short circuit current times the open circuit voltage times the fill factor divided by the power in. Okay. So I'll just mention briefly, I told you I was going to fly through these, and I'll do it a little more slowly tomorrow. But this idea of superposition, it's not immediately obvious why this should work. You know, so the idea is we take this light-generated current, we take this dark IV characteristic of the diode, and we just add the two, and we say that's how the solar cell works. So I'll say a little bit more about that in a minute or two. Now, there are going to be some non-idealities. You know, we're going to have a large p-n junction because we want to collect a lot of sunlight and generate a lot of power. there may be shorts here and there, shunt passages, leakage mechanisms, defects in the diode. So that would be a resistor, a shunt resistor that's in parallel with the junction. That's not good. It's going to lower the performance. The contacts themselves are going to introduce some extra resistance. That's RS, the series resistance. So if you do that, you can see here's the effect of taking that blue curve is the simulation of the device without any extra series resistance. If you add some extra series resistance in, you can see that it's lowering the current and the voltage at the max power point, or it's lowering the fill factor. So it's bad. You know, people worry a lot about that. The shunt resistance does the same thing. So you worry about these kind of defects a lot when you're trying to make high efficiency solar cells. Okay, so we run a simulation so you can see what the IV characteristic looks like. This is not a record 24% efficient cell, but it's not bad. It's 20% efficient. This is a typical thing you could do without lots of fancy, expensive processing. Open circuit voltage is about 616 millivolts. Short circuit current. Remember, what was that number? Anybody remember that? We said the maximum current that you could get if you absorbed every photon above the band gap and collected every one of those was it 42 or something?
44.
44. Okay, so we get 39. So if we had a better design, we might be able to get a higher current. Fill factor is 0.83. We haven't added any extra. Have we added any extra series resistance in this simulation?
1 ohm.
1 ohm. So, 1 ohm, people worry, even 1 ohm is a significant series resistance for a solar cell. And that lowers the fill factor a little bit. We could get a little bit higher if we didn't have any. Okay, then I'm just going to wrap up here and say a few things, and we'll get a chance to discuss these in more detail in some of the other talks. So this idea of superposition. I told you that this was not maybe intuitively obvious as to why this should work. It really works well for silicon, and I'll show you this in my lecture tomorrow. But it's not so easy to explain why. And we just take this light current, we take the dark current, we add the two, and we say superposition says that this will give us the response when it's illuminated. Okay. Now, how can you justify this? If you have a system that's described by a differential equation, if the differential equation is linear, you can add solutions. Okay. Let's look at the differential equation that describe a semiconductor device or a solar cell. All right. Here they are. The first one is divergence D is equal to rho, the charge density. This is Gauss's law. The second one is divergence current density is equal to generation minus recombination. The third one is divergence of whole current is generation minus recombination. The currents are given by drift diffusion equations. We have expressions for the recombination rate. The point is we have 3 coupled nonlinear partial differential equations. It is really not obvious that you could take the solution in the light, you could take the solution in the dark and add them. There's no reason to expect that would happen from these equations. Now, it turns out that you can, and I'm still searching for a simple explanation of why this works so well in silicon. We'll show you some simulations that show how beautifully it works. But to try to explain why it works takes a little bit of work. There have been a few papers about this. I haven't been able to boil it down to a one-line explanation. They can establish some conditions under which, if these conditions hold, you can expect to see superposition. But there are many solar cells, especially thin film solar cells that contain more defects than high-quality crystalline silicon, for which superposition does not apply. Now, we should talk briefly about efficiency limits. What determines the limit efficiency? So we have only 3 things to think about: short circuit current, open circuit voltage, and fill factor. If we can understand those 3 factors, we can understand efficiency. The fill factor is just determined by the shape of the IV characteristic, which is the diode characteristic. That's pretty fundamental. We can't change that very much. We can make it worse if we have too much series resistance. So we'll spend a lot of time trying to reduce series resistance. Now, the short circuit current. Well, the smaller the band gap, the more photons I can absorb from the solar spectrum. So the short circuit current strongly depends on the semiconductor that I've chosen. If I've chosen a given semiconductor, then I have to work hard to minimize the reflection of photons from the top surface, to maximize their absorption in the layer, and to minimize their recombination. Now, the open circuit voltage. So the open circuit voltage has something to do with VBI, and VBI it goes as proportional to the band gap. So what you'll find is that as you increase the band gap, the open circuit voltage increases. So there's a very classic paper that if you work on solar cells, everyone needs to study, the Shockley-Queeser paper, because this is a very famous paper where back in 1961, they did a calculation to try to determine the theoretical upper limit efficiency of a solar cell. And they did it so well that everybody has used it ever since. But the results are kind of intuitively easy to see. If you have a smaller band gap, the smaller your band gap, the higher the short circuit current. So what you're seeing on the bottom axis, on the bottom that's a normalized band gap. On the top you can see it in electron volts. As you increase the band gap, the efficiency gets better and better because you have more and more photons that you can absorb. Okay. Now, larger band gaps give higher voltage. So as you oh, I'm sorry, I did the opposite, didn't I? As you increase the band gap, you have fewer and fewer photons that you can absorb. But the open circuit voltage is increasing. So that's why the efficiency goes up. As you keep increasing the band gap, the voltage keeps going up. But the number of photons that you can absorb goes down, so the current drops. So there's some peak there, there's some optimum band gap where you're extracting, for that particular band gap, you're getting the most photons that you can get at the highest voltage that you can get. It turns out that that peak, look how nice that is. That peak is just a little above 1 electron volt. You know, that's silicon. You know, so it turns out that silicon is very, very close. You do this calculation a little more carefully. It might be a little bit above. Gallium arsenide is also very close to the optimum. So if you're going to pick one band gap, you'd pick something around just a little above 1 volt, give you the best efficiency. And you can see the numbers here. The best that you could possibly get is a little over 40%. I think people have refined these calculations, and the optimum is felt to be a little bit lower than that now. But it's up around 40%. So when you're doing solar cells, you know, there are three things you're basically trying to reduce the cost of producing electricity, because that's what's needed in order to make solar cells economically viable. So one thing you can do is to have very high efficiencies, but it's usually very expensive. You saw that Martin Green cell that I showed you. Processing that is very expensive. You can try to produce cells that have good enough efficiency, but at very, very low cost. And then you would use cheaper materials, thin film materials, polycrystalline materials that you don't have to epitaxially grow and that are very expensive and take high temperature processing. You know, a third approach, which is really related to the first, is you could use concentration. And the idea there is you spend a lot of money on a very high efficiency small cell, and then you have a very big set of optics to collect lots of solar energy and focus it down on that. So most of your expense is in the optics to focus it down onto a smaller cell that you can afford to make more expensive. So those are the three general approaches. And the thing that people are after these days in trying to solve energy challenges is something you call grid parity. And they go through these economic analyses. And in order to get electricity that's at 5 to 6 cents per kilowatt hour, you need to have a system that you need to install a PV system at about $1 a watt. So if you build a 100 megawatt system, it will cost you $100 million. And if you can do that, then all of the costs will translate. You can charge 5 to 6 cents per kilowatt hour, and it can be competitive with other sources. And the system includes more than just the solar cell. So you package all of these solar cells and you wire them up into a module, and then you have to have power conditioning electronics to take that fluctuating DC that comes out and put it into AC and put it onto the grid. And you have all of these, you have to install them, and you have to clean them, and you have to do everything else that it takes to maintain them and operate the system. Now the current costs, 2011, are about $3.40 per watt. So that's a long ways from where it needs to be in order to be economically competitive. If you just look at what's happening in the improvement in manufacturing processes, by 2016 it should be down to $2.20 a watt. But that's still more than double of where it needs to be competitive. So this is a big research challenge that people are looking at. These are some numbers from the Department of Energy, and they're sort of showing you in 2010, this is where we're at. In 2016, that's where we're projected to be. And this is where we need to be to start being competitive. And you can see how it's broken down into the power conditioning electronics are very efficient. That only contributes 10 cents, or contributes 22 cents now, and it has to drop in half. But the cell part has to get down to 50 cents per watt for the module. So that's not just one cell. You hook a set of cells together in a module. You package them, encapsulate them so that they'll last for 30 years. The efficiency drops a bit after you do all of that. You've got to be able to do that module at 50 cents per watt. We're at $1.70 a watt now. So more than a factor of 3 reduction is needed. So that's the challenge. It's different from those of us who work on integrated circuit chips and things where, you know, the value added comes because you put it in an expensive product. The cost of the chip is not that much. Or, you know, the manufacturing, you know, you add the value in the design of a complex microprocessor or something, and the manufacturing costs are a relatively small fraction of the overall cost. We're just dealing with a PN junction here. The manufacturing costs are really crucial. Okay, so a summary. The solar cell is really very simple. Light is absorbed, produces electron-hole pairs. The junction separates those electron-hole pairs, sends the electron out the N contact, the hole out the P contact. That current source, as it's flowing in the external circuit, induces a forward bias voltage that reduces the total current. The output power is short circuit current times open circuit voltage times fill factor. And as I just mentioned, everything is about cost in photovoltaics. Okay, so I can point you to a couple of references if you want to get a broader overview of the field, and I'll stop there and see if I haven't worn you out, if there's a question or two, I'll try to answer it. We have one down here in the front.
Thank you. And I wanna, if it's possible, please go to slide 24.
Which slide?
Slide 24. You talked about
slide 24. Let's take a look at slide 24. See, I got through all 69 of my slides. So. And most of you are here. I'm going to tell my wife that. Oh, that's not the one. Which?
Yeah, here.
Oh, I might have done some editing since I passed that out. Yeah, okay.
You said this equation is called ideal equation, yes? And we have non-ideality in our layers, yes? How do you treat with non-ideality, and what kind of non-ideality we will have?
Yeah, so I will say a little more about this in my next lecture. Yeah. So this is what people call the ideal diode equation. And what they mean by that is that all of the recombination processes are the kinds of recombination processes that I talked about. Carriers are recombining in the neutral N or P region. Carriers could also recombine in the depletion region. And that gives an N equals 2. Now, there are lots of other non-idealities that we could talk about, tunneling through defects and things could get very complicated. But
you think how much it would really affect our simulations? How much it would be changed? 10%, 5%, or 50%?
Oh, no. I mean, especially when you look at these low-cost photovoltaic materials where you have thin films of polycrystalline material processed at low temperatures, there can be high levels of defects, and there can be many of these non-idealities, and it can be impossible to see an N equals 1 component anywhere. I mean, that can be the whole game.
I have a couple of other questions. Can I ask
Yeah.
now or later?
Well, we'll see. Well, maybe we'll come back to you if we have some. Yes, we have a.
Yeah.
Sir, I have a question regarding the efficiency of the solar cell for that which is the expression. In that, it depends on short circuit current and the voltage. How the carrier, the current connection across the electrodes will affect the efficiency. So, is there any factor which accounts for that? Also, the efficiency term.
Yeah. So I guess the question is, what role does the charge collection efficiency play? And if it's less than so we can easily take the solar spectrum, and we can say, we can compute from that solar spectrum how many electron hole pairs are generated inside the solar cell. So the best we can do is to collect every one of those, and that would give us a short circuit current of 44 milliamps per square centimeter or something for silicon. Now in practice, we lose some by recombination. And I'm going to say a little more about that in my next lecture. So in different types of cells, sometimes people design a cell where all of the generation comes in this junction region where there's a strong electric field, which can take everything and quickly sweep it out to the right contact. There are other things you do to try to have minority carrier mirrors, so you make sure that the electrons don't diffuse to the contact and recombine there. You turn them around and have them diffuse towards the front. But there's a lot of solar cell design is all about trying to maximize that collection efficiency. Yeah. That's going to be my message on my next lecture. It's just recombination and generation. That's all there is to the solar cell. Right.
So solar energy is free. So why is the unit given as the cost given as dollar per watt? It should be a dollar in a lifetime of the cell.
All right. I'm not sure if I exactly got. Solar energy is free. I heard that, right?
The cost we are predicting for solar energy, harnessing solar energy is dollar per watt.
Mm-hmm.
So I'm not getting why it's dollar per watt, because once you make a solar cell, the cost is fixed. That won't change with how many watts are harnessed.
Yeah. So I may ask Professor Agarwal to comment on here because I think he's more of an expert than I am. But I know people that do this economic analysis, they'll make some assumption for what is the lifetime of this solar array. And, and when you back all of that out, they say, okay, if we can build the initial system for $1 per watt, we can build a 100 megawatt system for $100 million. And if it has their assumed lifetime, which is going to be 20 or 30 years, and they do all of the other cost analysis, then they can make an economic case that they could charge electricity for 5 to 6 cents per kilowatt hour. So there are a lot of assumptions. Reliability is a really important factor in these solar cells. Because if it lasts for 30 years instead of 20 years, it's much easier to make the economic case. You just made that one-time investment, and then the longer it lasts, the cheaper the electricity you produce is.
So,
Is that on?
I don't know.
Yes, it is, if you hold it close enough to your mouth.
So when the high energy photons are absorbed by a photovoltaic cell, some of the energy is lost to photons, right?
Yeah.
And that's basically heat inside the device, right?
Mm-hmm.
People work on using thermoelectric principles to extract some of that excess heat.
Well, you should know that. You're from MIT, right? I just saw a paper in, was it Nature or Nature Materials, maybe last week from the Gang Chen group, which is on my laptop to try to read. So my understanding, I just looked at the title and I thought, oh, this sounds interesting. So my understanding is that he's trying to take this waste heat, that for a solar cell, this is just waste, right? And to take that waste heat and couple the solar cell to a thermoelectric device and convert that into electricity and get a little more power out of it.
Is it on a separate module?
I don't know.
The thing is, if is showing up at the junction. You've already got a P ligand anyway, right?
Yeah.
It's really, it looks very much like just a different reservoir in which you're drawing the thermal separation.
Yeah. I'm a little, the efficiency of thermoelectric devices is not that great, but if you get it for free, you've got that heat there, and if it doesn't increase your manufacturing cost by much and you can get another 1% or even few percent out of it, that would be very useful. Yeah. So that's a good question, right? So it connects this lecture with the previous 2 lectures on thermoelectric devices.
So one question I have is like, how does this high energy carrier affect the efficiency of the electric current that we get? It's just the high kinetic energy that we lose?
Yeah, so what happens, we talked about energy relaxation time in the last lecture. So what happens is these carriers very quickly, in picoseconds or a few tenths of a picosecond, shed all of this excess energy and just relax down to the bottom of the conduction band. And generally that happens so fast that when we think about current flow, we don't even have to account for those processes when we're looking at steady state currents and things. They very quickly thermalize. Right.
So, but still we will be able to collect those electrons, so we will get the electrical current.
Yeah, you get the electrical current, but you don't get all of the energy because they've dropped down, they've dropped down to the band gap, right? Now you've lost all of that. You've lost some portion of that energy that they had. That's the whole idea of using tandem junction solar cells, multiple band gaps.
I was just wondering, have y'all thought about adjusting the size of your P and N junction? Is there a certain standard that's regulated? I don't know. Have you thought about
the size of the PN junction? Well, so you need large.
Your solar cell capacity or what you're holding, your P and N junction. I just wondering, is there like a certain standard or like an ASTM or that?
Well, basically you want to collect light from as big an area as possible, so that you would tend to think I want as big a PN junction as I can get. Now the difficult, so there is.
It was regulated or is.
No, not that I know of, but there's something related to that. Maybe I could I could point out. It might come up in the lecture tomorrow. I'm looking for my Martin Green cell here. Now this is really a nice example of solar cell engineering. You'll notice how small, there's a small p-type contact on the end. There's also another variety of solar cell that also gets near record efficiencies, where the end layer is a small thing like that. They call them point contact cells. So there's a big piece of silicon, it might be either N-type or P-type, but the P-N junctions, the N region and the P-type contact are very small. So they're trying to minimize the size of the P-N junction. So it's mostly absorbing materials. These P-N junctions are very small, so the carriers can diffuse to them and get collected. But there's a lot of recombination and things that happen in the P-N junction. So if you can minimize that, those are called point contact cells. Now, the area of the cell can still be very big, but the area of the P-N junction itself can actually be quite small. Okay. All right, are we ready for a break?
Yeah.
Oh, no, oh, yes, okay. See, you're keeping all of these people from a break, so I don't want to put pressure on you, but it better be a great question.
Page 38, yes.
Pardon me?
Page 38.
Slide 38?
Yes.
All right, let's take a look at slide 38. Now, is that the right one?
Yeah.
Yeah.
Here for silicon, we need that because it's indirect band gap, we need photon. Yes.
Yeah.
I was thinking that because it generates heat when we have higher energy with photons, when it's absorbing, it makes it a little bit warm. It makes the solar cell warm. Yes. That kind of heat could help this kind of solar cells to work better, or the direct band gap would work better.
Yeah, I'm not sure I exactly understand the question. There actually is a direct band gap in silicon, right? There is a conduction band that's up there in higher energy, and the higher energy photons can be absorbed by that direct process. Yeah.
My question is, direct band gap is better or indirect band gap? Which one is better?
Oh, I think direct band gap would be better, yeah. Because it would take less, everything is about cost. Even if you can minimize the materials cost and you can absorb all of the photons in a very thin layer, it's always best to have a direct gap, yeah.
And the other question is, what is shunt resistant?
Pardon me?
Shunt resistance.
Yes, yeah. It is some parallel current flow path. It might be a defect. You might have a crystal defect that goes right through the junction and just kind of shorts it out. You might have had a pinhole in your process, so when you deposited the metal contacts, a little bit of metal went down and shorted out. There can be all kinds of extraneous current paths, that are, can only be bad, right?
Thank you.